Back in first quarter, you learned about arithmetic sequences. That is when you would add or subtract something from one number to the next. We're now going to talk about in section 6.6 about geometric sequences. So here's what you're going to learn. You're going to learn how to identify them, extend and graph geometric sequences, and then write them as functions. The core concept of identifying geometric ratios says that in a geometric sequence, the ratio between each pair of consecutive terms is the same. This ratio is called the common ratio. Each term is found by multiplying the previous term by the common ratio. So 1 multiplied by 5, multiplied by 5, multiplied by 5. Each of these is being multiplied by 5. 5 is the common ratio. And these would be the terms of the geometric sequence. Example number 1. Let's identify that geometric sequence. Decide whether each sequence is going to be arithmetic, geometric, or neither, and explain your reasoning. So in the first example, 120, how do you go to 60 to 30 to 15? You multiply by a half. That's it. So, is it arithmetic, geometric, or neither? Well, since you're multiplying, it's geometric. And the reason is because the common ratio is 1/2. Now in the next example, 2 to 6 to 11 to 17. Well, 2 times 3 gives us 6. Well, that doesn't work. And then you could say, well, if I add 4, now that doesn't work either. So you would say that there is no common ratio, so the sequence cannot be geometric, and there is no, do you remember what we called this? It's not the common ratio, because the ratio is when you're dividing. Like here we divided by 60 divided by 120, 15 divided by 30, divided by, each of them give us a half. Here, we do not have a common difference. The common difference would mean that the sequence is not arithmetic. Therefore, this sequence is neither arithmetic or geometric. Geometric, once again, remember, is the common ratio. Arithmetic is the common difference. So in the second part, we're going to extend and graph geometric sequences. Example number 2. We want to write the next 3 terms of the geometric sequence. A, you'll notice that the common ratio is timesing by 2, multiplying by 2. So the next 3 terms would be 24 times 2 is 48, times 2, multiplied by 2. And the next 3 terms, when you multiply by 2, would give us 48, 96, and 192. Pretty easy. In B, what are the next 3 terms? Well, what's happening from 64 to negative 16 to 4 to negative 1? What is your common ratio? Hopefully, you're realizing that you're multiplying each time by negative 1/4. If you multiply by negative 1/4, negative 1 times negative 1/4 gives me positive 1/4. Times negative 1/4 would be negative 1/16. And once again, following the same pattern, would give me positive 1/64. So the next 3 terms would be 1/4, negative 1/16, and 1/64. So far, pretty easy. In example 3, we're going to graph the geometric sequence, and then I'm going to ask you what you notice. Now, when we actually make a table here, this is one thing that a lot of students forget. And a lot. The first term is always the position of the term. So position, I'm just going to let n be the number of position that we're talking about. And then the term, which is the number in your sequence, I'm going to let be a sub n. Now the position, the first term, the second term, the third term, the fourth term, the fifth term. Here they are. Now, if you graph them, what would you get? Hopefully you realize, what do you notice? You're noticing that we have an exponential function, or we have an exponential curve. This is being cut in half every time. Now, once again, it's important to notice that as we go down, you get closer and closer and closer to the x-axis, but you're never going to cross it, because if you keep dividing by 2, you're never going to hit 0. So the asymptote, which you'll learn later, is going to be y equals 0, which is the x-axis. So it's this line. It's approaching y equals 0 the entire time. Now we're going to write geometric sequences as functions. We're writing them as functions. So because consecutive terms of a geometric sequence have a common ratio, once again, each number in consecutive order of a geometric sequence has a common ratio. You can use the first term. That's why we call it a sub 1. And the common ratio r to write an exponential function that describes a geometric sequence. So, position, this is the first number in the sequence, the second, the third, the fourth, and then it's called the nth term. Now that actual term is a sub 1, a sub 2, a sub 3, a sub 4, and a sub n for the nth term. The position is what we plug in for n. Now written using it together with r is the common ratio right here. R, remember, what do we do every time? We multiply it. So we take the term, look what it is, we take, to find the second term, we take the first term and multiply it by the ratio. We take the first term, we multiply it by the ratio, squared. We take the first term, we multiply by that same number again. Remember, this is really what you're doing. You're taking a sub 1 times the common ratio. Then the second term times the common ratio. You keep multiplying by that common ratio. But that's why we're using exponents here. So you'll notice the relationship. The fourth term has a power of 3. The third term has a power of 2. The second term has a power of 1. What are we doing each time? We're subtracting 1. And that's how you get this expression. The first term times the ratio taken to the number of terms we have minus 1. Which gives us our core concept. The equation for the geometric sequence, here it is. I want you to understand what this means, because I know you look at this and you're like, okay, seriously, this doesn't make any sense to me. Here's what it says. We're going to let a sub n be whatever nth term we're talking about. So if I want to find the fifth term, then this would be a sub 5. If I want to know the seventh term, I do a sub 7. You take the first term times the common ratio to whatever the number of term is minus 1. Here is your study tip. Look at that. Notice that the equation right here that I'm pointing to is in the form y equals mx plus b. You're like, how in the world is that equal to the same thing? I'm sorry, not mx plus b. Y equals a b to the x power. Remember, that's your exponential function. There's your a. That's your first term, what your initial amount is. This is what you multiply each time, which is, in this case, your common ratio. And x is your exponent. It's in the same format. Example number 4 is finding the nth term. So this means you can find any other term you want, given the first terms of a sequence. So here we go. 2, 12, 72, 432. Absolutely, if you want to continue on to see what the 10th term is, you're more than welcome to do that. But you are in an algebra class, so we need to use algebra. We have to write a function. We have to write an equation. So we're going to start by writing down our equation. A sub n equals our first term times the ratio to the n minus 1 power. It looks difficult. It's not. So our equation would be this, a sub n. This does not change. You leave it as a sub n. Equals our first term. Our first term is 2. Times, parentheses, our friends. R is just the ratio. What do you do to go from 2 to 12 to 72 to 432? You multiply by 6 every time. So that's your common ratio. And then the n minus 1 just stays there. Bam, you're done. You have 2 things to plug in. Those 2 things are the first term and the common ratio. Now the next part is finding what the 10th term is. So you take a sub 10. Here's what you do. You plug it in. Equals 2 times 6 to the 10 minus 1 power. That would be a sub 10 equals, do not multiply 2 times 6. That's illegal. 6 to the 9th power. So you take 6 to the 9th power, you times it by 2. So the 10th term would be 20,155,392. So now you can rewrite the equation for a geometric sequence with the first term a sub 1 and a common ratio, and we can write it as a function. Function notation, all we do is take the a of n, or a sub n, and we plug in f of n. So it becomes that. The domain of the function is the set of all positive integers. I can plug in any number I want for the domain. The range, however, is not going to be that, but we'll talk about that a little bit later. Example 5. Clicking the zoom out button on a mapping website doubles the side length of the square. So bam, we keep enlarging it. We've done that before. We've hit one of these arrows to increase or decrease the size of a map or something that we're looking at. After how many clicks on the zoom out button is the length of the map 640 miles? The first thing we have to do is this. Now I want you to write this down because I'm going to take it off the screen so I have enough room. So make sure you write down this chart and the 640 miles. The first thing we're going to do is just write down our function notation. Here it is. F of n equals a sub 1 r to the n minus 1 power. All I do is find the first term, which is 5. I plug it in. The common ratio is multiplied by 2 each time. I plug it in. Here's my function. That's it. That's part 1. Part 2 is going to actually use that and solving it. So let's solve it. I'm trying to find it here. Let me find it. Solving it would look like this. Found it. All right, so here we go. There's a lot of work here. This is the function. It represents the geometric sequence. So I'm going to solve it by graphing. Use this function to find the value of n for which f of n equals 640. So all I do is plug it in. Bam. I want it to be 640. I plugged it in right here for f of n. Now to solve it, I am using graphing. I took y equals one side and y equals the other. I plug them in my graphing calculator. Here they are. Y equals 640, and here is y equals 5 times 2 to the n minus 1 power. I use the intersection button to find this. Now, we already know 640, so 8's what I want. So after how many clicks? After 8 clicks, it would give me a map of 640 miles. But wait, we're not done. You can solve it a different way. If you want to do it algebraically, look at what I did here. I plug it in. I love this. This is what's amazing with being in TAP and TAP students and being able to manipulate equations. Look what I did. I can get rid of a times 5 by dividing both sides by 5. I now have two different bases, 128 and 2. I can rewrite them as the same base. So I can take 2 to the 7th power, which is the same thing as 128, equals 2 to the n minus 1 power. I now have the same base. I write the equation 7 equals n minus 1, and I can get n minus 8, which would also give me the correct answer. Amazing.